So in our next video, we're looking at substitution and the exponential functions. And there's two of those that we're going to look at. Let me just go ahead and pull those up for you right quick. So we have the integral of e to the x dx and the integral of a to the x dx. And of course, e to the x is just a special case of a to the x, okay? So we're really and truly, probably what we should do is where we see these two integrals, e to the x and a to the x, if I could go in and maybe modify these a bit to say the integral of e to the u du is equal to e to the u plus c, right? Then we would have the integral of a to the u du is equal to a to the u over ln a plus c, right? So again, we're using substitution to do these, and it's important to be able to identify what is u and what's du and make the appropriate substitutions. So let's take a look at this problem here. We've got the integral of 2x e to the x squared minus 3. Again, we talked about it back a couple of videos ago where we wanted to see or wanted to give you a hint as to what u should equal, right? So in this case, u is pretty set. I mean, it's pretty standard, right? So u is going to equal the exponent, is spell that right, exponent of e or a, whatever the case may be, whether if we have e or some other constant. And we'll look at an example of this one in just a minute. So again, looking at this problem that's on the screen right now, if we just focus on this one, I think it's pretty easy for you to see that the exponent for e is x squared minus 3, which makes du 2x dx. So I can easily identify there is my du, right? So I can make that appropriate replacement. I don't have 2x dx anymore. I've replaced that with du. And I don't have e to the x squared minus 3 anymore. I replace that with u. And then, of course, we defined the integral of e to the u du to be e to the u plus c. And it's just a matter of plugging back in. That's kind of tiny. It may be hard to read. So we have the integral of e to the u du, which is e to the u plus c. And our answer is going to turn out to be e to the x squared minus 3. You don't have to put this in parentheses. I just did to really separate what was going on there so that you're not confused as to what that might be. So e to the x squared minus 3 plus c. Here's one. So this is the one I wanted to do where we had to identify what a was. And in this case, I think you can see that a is 2. It may not be obvious, right? The square roots of x may be throwing you off a little bit, but we have the integral of 2 to the square root of x, right? And that's your clue that this is an a to the u du problem. So a is 2. That makes u the square root of x, or x to the 1/2. Recall that the square root of x and x to the 1/2 are the same. So the derivative of x to the 1/2 is just x to the negative 1/2 dx. So again, we can manipulate this just once or twice more. I'm going to have dx over 2 square root of x. Okay. Now, one of the things that we can do is identify real quickly that we have the square root of x on the bottom right there. So we've got dx over square root of x. So what I'm going to do is move this 2 up here with the du. That allows me to rewrite this problem. Instead of having 2 to the square root of x, we're going to have 2 to the u, okay? And instead of having dx over square root of x, we're going to have 2 du, again, because dx over square root of x is equal to 2 du. This 2 is a constant, and I can move it outside the radical, which is what we show right here. And then we're left with the integral of 2 to the u du. Applying our formula gives us 2 times, so this 2 out in front, right, is this guy. So we have 2 times 2 to the u over ln 2. Again, we're just applying that integration formula that we saw earlier in this PowerPoint. So this is the integral of 2 to the u, and then we're adding that plus c. So there are some rules for logarithms and things like that we might want to bear in mind right here. So I can replace u with the square root of x. And I'm just going to move this out to the side and put this 2 up in its place. So 2 over ln 2 times 2 squared of x. So really what's going on here is we've got, excuse me, I put that u in the wrong place. So I have 2 times 2 to the u times 1 over ln 2, right? That's another way of expressing this right here. And it makes it a little more obvious as to why we would put the 2 over ln 2, because we're going to have the constants together with that 2 to the square root of x. Okay, so here's another one where we've got some issues, right, with got to find the antiderivative, and it looks really intimidating, but again, if you'll just take a moment and look at what you've got here, we've got an exponent of x squared over 2 minus x, which makes du equal to x minus 1, right? The 2 comes down and cancels with the 2 on the bottom. X minus 1 dx. So in my problem, I have that x minus 1 dx right there. And so this really just turns into an e to the u, okay? So again, we're replacing, we're going to replace dx with du over x minus 1. So let me show you how that works right here. I'm going to divide both sides by x minus 1. And that's equal to dx. So if we take our integral over here, and we've got x minus 1 e to the x squared minus x times dx. Okay, so remember, we're replacing dx with du over x minus 1. Well, now those x minus 1's cancel. And we've just got e to the, that whole thing is u, e to the u du, or e to the u plus c. And we plug that u value back in, so e to the x squared over 2 minus x plus c. Here's one that's really, really unique. We'll end up with this one right here. We've got the integral of secant squared x e to the tangent x dx. And this is not an indefinite integral now. This is a definite integral. So remember, we're going to change those boundaries, right? And you can see how we've done that here. We have new boundaries of 0 and 1, and we can talk about where those boundaries come from. So if you were looking to say, okay, well, what is step 1, Mr. Stark? I'm not really sure what to do. So step 1 is to identify what is u. Step 2 is going to be to take the derivative and figure out what du is. And then step 3 is to make those substitutions. You got to make the appropriate substitutions. If you don't do it the correct way, you're going to get the wrong answer. 4, the next thing we're going to do is change our boundaries. Change the boundaries, and that's where we get the 1 and 0 from. And then the last step is just evaluate the integral. So the question then becomes, well, what on earth is u going to equal? Because all I see is a bunch of letters, and it's almost like somebody's writing a book and I just can't read it. Well, remember that u is going to equal the exponent for e. So u here is equal to the tangent of x, which makes du equal to secant squared x dx. If you're wondering where that secant squared x came from, we're taking the derivative of tangent, okay? So this brings up then what my problem is going to look like. Okay, so secant squared dx gets replaced by du, and tangent x gets replaced by u, so we have e to the u du. So I've figured out what u is. I found du, and I made the appropriate substitutions. The last thing is to change those boundaries. We're going to change the boundaries by doing this. We're going to let u equal 0, and we're going to let u equal the tangent of pi over 4, right? So we're getting those values from here and here. Now, according to the unit circle, the tangent of 0 is equal to 0, so that gives us this boundary of 0 right here. According to the unit circle, the tangent of pi over 4 is 1, and that's where we get this boundary. So we're going to have e to the u evaluated from 1 to 0, which is e to the 1 minus e to the 0. Recall that e to the 1 is just e, and e to the 0 is 1. Okay. And so here's one more problem where we give you a definite integral again. You can take a look at that one. Let me know how this goes. If you need some additional resources, I'd love to hear from you and supply you with what you need.